Hello Year 9, hope you're all well. This is the first lesson I put together for just our class. As you can see, my lab looks a little bit different this week. I thought I'd start by recapping the work we did before Easter on electricity supply. And as you'll see, I'll work through these slides, and at the end there are a number of tasks that I set that you can dip in and out of and complete as you wish. Okay, so let's start with the difference between AC and DC. AC stands for alternating current, and this means it's the direction of the current which is alternating. So the current will flow one way through the circuit and then the other. So if we look at a CRO trace, where it's above the line there, we've got positive direction, and then it switches and goes in a negative direction. AC is the supply we get to our homes at 230 volts and a frequency of 50 Hertz. Don't forget, frequency means the number of cycles per second, so the number of times the direction is changing in 1 second. DC then is direct current, which means that the current continually goes in one direction, hence we get the flat line on the CRO scan. Battery supply DC current, and if you think about the power packs we use in the lab, obviously we can choose AC or DC on those. We can vary two things about our AC current. The first is the amplitude. Amplitude is the height of the wave. Be careful here, because by height we mean the height above that black dotted line, which represents 0 volts, or when nothing is actually happening. So as the current flows in one direction, you can see it goes below the line, negative direction, and as it goes above the line, it's going in a positive direction. So the height of the wave, or the amplitude, is the height of it above that dotted line. The taller the wave, the higher the voltage. We can also vary the frequency. We have 50 Hertz to our homes, but actually you can have any kind of frequency. The higher the frequency, then the more quickly the current is changing direction. And we can see that on the CRO scan there, because the more frequent it is, the more oscillations we get per second, and so the waves appear to be bunched closer together. As well as frequency, we can measure the time period of our alternating current, and the time period is how long it takes for one oscillation to pass, or one wave to pass, measured in seconds. Now, if we look at the screen here, you can see that for one wave or one oscillation, we mean the sort of start to finish of the wave. So on the top two arrows there, I started at the top of the wave, I've gone down and up and finished at the top of the wave again. And there are 4 squares going along between the first and second arrows. If I look at the bottom, I've started the wave at the 0 line, and then it's gone up, down, through the 0 and back to the beginning again. And again, on the bottom 2 arrows, you can see 4 squares between the start and end of the wave. When I'm using the oscilloscope in the lab, I have something on there called the time base. And usually when I'm fiddling around with this, I'm trying to make sure that you've got a nice clear image with a wave sitting squarely on the screen, rather like the one in the diagram below. But in reality, the time base is there to set a scale. So it will tell me how much time each square along that scale represents. In this example, we set the time base to 2 milliseconds. Don't forget, little m or milli means 1,000th, so 2,000ths of a second. Going back to what we did in the last slide, we know that the time period is 4 squares across from peak to peak or trough to trough. So the time period is 4 multiplied by 2 milliseconds, which gives us 8 milliseconds. Or if I divide by 1,000, 0.008 seconds. We already know the word frequency means the number of oscillations or cycles per second. And in fact, it can also be calculated by using the formula frequency is 1 divided by time period. The two are related. So in our example, the frequency would equal 1 divided 0.008 seconds, or 125 Hertz. So that means we have 125 cycles per second. So to summarise, our mains electricity supply arrives at our homes at 230 volts AC with a frequency of 50 Hertz. Don't forget, alternating current constantly changes direction. I've highlighted the word direction there because that's the word we're looking for in an exam question, for example. And it produces what we call a sine wave shape on the CRO. Direct current or DC current flows continuously in one direction. Again, that word direction is key. So we get the straight line on our CRO. So continuing in our theme about domestic electrical supply then, the next thing we need to look at is the plug. We did a bit of this just before Easter when we wired the plugs up. And if you remember, there are 3 pins. There's the live, earth and neutral. They're all made of brass. Brass has got a lot of copper in, so it's a good conductor, but it's much harder. Copper would bend when you try and put the plug into the socket. So blue goes left, brown goes right, as you can see on the diagram here, and the earth one goes right up to the top. It's the green and yellow wire. The live wire is actually the one that varies in voltage from plus to minus 230 volts, because we're obviously AC. The neutral remains at close to 0. The neutral and the live are the two that make the circuit which delivers the current to your appliances. The earth wire isn't really involved in that. The earth wire is there as a safety feature. It's there to protect you in case something goes wrong with the appliance. If your appliance is made with a metal casing, so for example a metal heater, and the live wire became attached to the casing in any way, then if you touched it, the casing would be at 230 volts, and obviously that wouldn't be very safe. So the earth wire is there to protect you. What happens is if you touch the live casing, instead of the current flowing through you to the earth, which will cause you damage, it goes through the earth wire instead, and the earth wire has what we call a low resistance path, so it's much easier for the current to flow through the earth wire than you, which makes it much safer. The other safety feature is the fuse, which you can see is attached to the live wire, and this is there to protect the appliance rather than you. If a current coming through the plug is too high for the appliance, then the fuse will burn through. It will break the circuit protecting the appliance. The important thing here is that the fuse breaks the circuit and just switches everything off. It doesn't control the current. A lot of people use the word control, and it's wrong because it's not going to change whether the current is higher or lower. It's either allowing it through or it's not. So up on the top right, you can see a typical fuse, and in there you can see the little tiny wire in the centre that would burn through, and that's what we see in plugs used to protect individual appliances. That's in contrast with the picture on the bottom left there, and that's what we use to protect the circuits inside our homes. It's a fuse box. As you see, we no longer keep individual little fuses in that box, which we did used to do a long time ago. The problem then was that if you needed to replace a fuse, you had to make sure you had one in your home, and then you had to go and change out the old one and put the new one in. This is a much quicker and more efficient system, and they've called it an RCCB, sometimes also called an RCD, and it works more like a switch. It's very like the little button we have on the front of our power packs in school, where if you overload the current, it pops out and you have to reset it. The same thing happens here. The current coming into your home is too high, then one of these fuses, instead of blowing, the switch trips. And then to reset it, you just flip the switch back. Much, much simpler. So here's a typical exam question. You often get questions about electrical safety because it's obviously very, very important. And in this case, they're showing a kettle with an earth wire, live wire, neutral wire there, and they're asking us if a fault makes the metal case live, the earth wire and the fuse inside the plug protect anyone using the kettle from an electric shock. Explain how. And in this case, they're only offering 2 marks, which means they're not really looking for a very in-depth answer. Okay, so I divided the 2 marks between talking about the earth wire and the fuse. That means I'm going to hit both parts of the questions there. It's only 1 mark for each bit, so very simply at the top, they want you to say something about the fact that the current from the live wire ends up flowing through the earth wire. In a longer question, if it was a couple more marks, I would talk about the fact it flows through that low resistance path to earth. The second mark is for talking about the fuse. Here they simply want you to say that the fuse melts or blows or breaks. And in again, a longer answer question with more marks, I will talk about the fact that if there is too high a current flowing, mark 1, then the fuse will blow, mark 2. Okay, so now we've been through that. There's a couple of links here that you might find useful if you need to go over anything again. I put a sheet on Show My Homework with some questions and a mark scheme so you can check your own answers. And then finally, I'd like you to do the quiz so I can see how you're all getting on. If you fancy something a bit different, then I've downloaded or put on here a video from an A-level site. It's easily accessible to you guys though, about the twins paradox, something a little bit different. And as the night skies are very clear at the moment, have a look to the west this evening for Venus. It's a very bright object, it doesn't twinkle. If you've got an Android phone or device, you can also have a look. There's a really good app you can download that tells you where to look. Okay, that's all for this week.